I asked classroom services. It's like, no, there's no microphone in this room. It's like okay. So I was not happy about that response from them. Okay. So with regard to the next coming weeks, so milestones in the midterm, October 9th, Sam, your grad TA, will be giving you a lecture on LaTeX, and hopefully that will sort of encompass several topics that we've covered, including images, vector graphics, which we'll talk about more today, and basically creating a document using the LaTeX typesetting program. It's a little more involved than Word, but the quality associated with the type of document it generates is very compelling, and also it's well suited for formulas. Some people will try to use some of the formula maker in Word or LibreOffice, but nothing beats using LaTeX. And one of the things that it also does is sort of gives you a flavor for what programming or markup happens to be. So kind of similar to what some of the things that we looked at in some of those text files, the rich text file where you can actually read some of the formatting. LaTeX will do the same thing. So, and with regard to LaTeX, if you ever decide to write a document, particularly a dissertation or a thesis for your graduate work, I highly recommend that you do it in LaTeX rather than Word. There are some people who try to write their dissertation and documents in Word, and in my opinion, Word is probably good for about 10 pages. After that, it really starts dying, particularly if you've got a lot of images that you try to insert. LaTeX is much better for that. Books have been written in LaTeX, and it's a very straightforward way of generating nice documents. And a lot of the information that you have is in text files, so it's easy to sort of recover if something happens. Remember what we talked about, binary files? If you have a Word document, you save that out, and you try to recover it, what do you get? It's stuff that you can't read. With LaTeX, it's always stuff that you can actually consume. You can actually read all that information. Okay. On October 11th, I'll start distributing old exams. So make sure that you've got either all your swarm check-ins in place and also your spreadsheet. So those people are still having problems trying to get the IFTTT to Google Docs situation in place. Please come see me so we can try to sort that out. But based on the next couple of classes, I'll cut off the logging of your attendance, and I will distribute the exams based on that number. Right? Yes. What's that? Oh, if
yeah, like today I can't check.
Oh well, that's why you have a redundancy with actually going on to Slack and then doing a summary of the. Okay, so yes, I understand those things. That's why I try to be redundant with regard to attendance check. Okay, so if you even if you were not here, at least if you made that entry, it at least tells me it's like, oh yeah, they either watched the recording and absorb some information. So yeah, no, I try. My phone dies all the time too, so usually at the worst times. You have fall break, and that's probably a good time to try to catch up on some of the readings and the podcasts. Again, if you're traveling, some of those podcasts you may just want to download onto your phone and listen to it on a trip. But as far as reading is concerned, remember that you have the weapons of math destruction as one of the major topics for the exam. I've already finished making the exam, so it's all set. So that's something that will be coming soon. And the old exams should reflect basically what the new exam will look like. So I would suggest using that as a starting point for studying. On October 19th, I'm actually sort of a sort of serendipitous situation in that I've actually been able to get a hold of 2 alums of this class to come in, well, at least one of them, but possibly 2, who took this class and I just wanted them to come here and sort of give a retrospective of where they are now. Okay. One of them is actually a data scientist, and the other one just graduated from computer science, and sort of give you a sense of how they got to that point from this class. So sort of give you a sense of what was like, what were they thinking, what were their what they liked and what they didn't like. So I think it's important to sort of sometimes when you're sitting in here, you're kind of always asking, it's like, well, what good is this? And I think what they'll hopefully do is sort of give you a sense of where things that I teach you can lead in the future. Okay. On October 23rd, we'll review for the midterm exam for that class. So, and on the 25th, we'll have the actual midterm itself. So those of you who have alternate arrangements, please let me know so that we can actually get the exam to you or to wherever locations are necessary, and we'll work with that. Yes? Yeah, I moved it back just because of the that alumni retrospective from the 2 students. I think that's more important than the exam, to actually hear what the people decided with regard to some of the stuff they learned here. So, okay. All right. Yes.
Will there be content from podcasts inside as well as
Yes, there will be related contents to it. So just to give you some sense of it, so if you think about what Blair Tinker talked about in terms of geographic information systems, there's a lot of relationship with that with the geospatial revolutions video podcasts, right? So it's good to sort of look at that, look at what he presented in light of those podcasts, right? And also, since you brought that up, we'll actually jump into one of my, I don't want to say it's a favorite topic, but it's a topic that always has causes a lot of thoughts. And that is ta-da, trolley problem. So does anybody know what the trolley problem is? Psychologists would always know the trolley problem, but yes. So I'll elaborate on that, but that is the gist of it. But somebody get a.
There's like a family of 4 and like a constant person.
Okay. Along those lines, and we'll elaborate on that. Anybody else have heard this particular conundrum? It's kind of interesting because it does show a lot about, or just it illustrates, or it shines a light on human nature in general. So here's the first situation. So scenario 1. So you have a chance to save these people that are on the track from a runaway trolley. And in order for you to do that, you can flip a switch and save 4 people, but kill 1. Right. And that's something that people, 5? Oh, sorry, 5. 5, yeah, sorry, I can't count. That's why I got into computer science. So have the computers do accounting for me. So that's, and the thing is with this particular type of situation, a lot of people really have, they'll say, yeah, I'll do it. That's not a, it's you're saving 5 people at the expense of 1. And most people, flipping a switch is not an issue for them to do. Now, the second scenario is the following. So there's this huge person over the bridge, and if you happen to push them over and they fall in front of the trolley, that trolley will stop and save those 5 people. Okay. So the question now is, will people do this? What's that? Yeah, you can, but here's the thing. Will most people will not push this person off the bridge to save the 5 people, right? Because there's something about the physical contact, physical action of actually doing it, whereas the previous example where you flip a switch, you don't really have any contact with that person, so you're less likely to actually do that. And this is something that people have been posed in the past, and people will, just because of the actual act of pushing somebody is something that people will not tend not to do. Yes.
The thing is, if they're big enough to stop and move in a trolley, there's no way I'm going to be able to push them.
That's a good point.
Well, yes, but it's basically yeah, conceptually. But the idea here is that what we're saying with these kinds of problems actually relates to some of the podcasts with regard to drone technology. Right? So if you look at that, a lot of people now in the Air Force, don't even go to the theater, the theater of battle. What they simply do is go into this shipping container, and they actually control drones halfway across the world and essentially kill people simply through the act of pushing a button and sending off the Hellfire missiles towards certain targets. And the question is that something that is that something that you want people to be able to sort of say, yeah, it's no problem. It's just pushing a button and not really understanding the impact of what's going on. And I think that's something that needs to be kept in mind, because there's a lot of things that we do in technology where people just become numbers, right? And that's something that we actually see in weapons of mass destruction, is that you treat a lot of these people as being numbers and not really taking into account what are the actual situations associated with these people. It's something that's that has to be well, I don't have a solution for that, but it's something that needs to be kept in mind by people who use technology. It's like, you always have to ask yourself, who's being hurt by this, right? And are we going to allow that to happen? And in some situations, people are probably okay with that, but it's something that always has to be asked, and not just let the algorithms sort of take care of the decisions. And I think we sort of see that a lot in weapons of mass destruction. There's always that possibility of harm being inadvertently placed on people simply because you don't see them as people, but just simply numbers. Okay, trolley problem, drones. That's actually something that and also there's the situation with regard to becoming more and more of an issue with self-driving cars. What are the kinds of decisions, as a programmer, what are the kinds of decisions that need to be made? Do you save the person on the motorcycle without a helmet, or do you save the person on a motorcycle who has a helmet? Do you save the person in the car, or do you save the people, all the children in a school bus? Certain type of situation. Those are kinds of decisions, although it seems philosophical, that actually, when we start getting into these types of technology, have to be made by programmers. They have to give thought to those kinds of situations, which before we didn't really have to. Okay, if something happened, it just happened. But now we have technology sort of taking over and trying to understand what needs to be done in those types of situations. How should we make those decisions? And one of the things that I also want to point out with technology is that it's neither right nor wrong. Any technology that you deal with is not really has no basis in terms of morality. But one thing that you have to keep in mind is that technology has bias, because somebody developed an algorithm, developed that technology, and because they're human, they've actually associated some sort of bias with that technology. So that's something that you need to keep in mind, is that just because technology is not unbiased at all, but very much dependent on what the person's thoughts are in terms of developing an algorithm. All right. So back to less depressing topics. And last time we were looking at this in imagery. And Gabby was able to ascertain that it was ASCII. The previous slides. Okay. That represented ASCII values. So if you recall, it was 42, 52, 62, 72, 82, 92 for the gray values. And we left it here and said, well, how does this star relate to this pattern? And it is related to ASCII values. I'll take a stab at it, Gabby. You don't know? Okay. All right. That's okay. So 1, 2, 3, 4, 5, 6, 7, 8. So let's actually see where that is related. So we said that star is the number 42, correct? And if we go into sheets, and we say something like the following. Come on. We say. So new spreadsheet. Okay. So 42. Come on, Mr. Spreadsheet. Help me out here. clicking it. It gets slower whenever I click it. Come on, load it up. Right. 42, 52, 62. Working. It's crazy. Oh my goodness. Anybody have a question while I'm waiting for Google to catch up? All right. It's not working. Let's go to another tool. This will actually be supposed to be a next class's lecture, but I'll start it anyway. So in Wolfram Alpha, technology up at its best. What's going on with that? You're making me feel better. Yeah. Where's everybody? How's everybody else's wireless? I am not connected.
You know that even like a few of our have like several different like wireless, so on certain networks you can't reach like.
Yeah. Well, it really. I think they had a wired connector here before, but I haven't played with. I keep forgetting to bring a cable for that. Oh my goodness. Crazy. Craziness. All right, so come on. It's nuts. He who lives by wireless dies by wireless. 42. Yeah, I don't know what that is. Thanks. .42 binary. Show us the pattern. 1 0 1 0 1 0. So it'll be 0 0 if this was 8 bits. So let's take a look at what we had previously. Zero zero 1 0 1 0 1 0. Let's look at 52. What you were going to guess?
Yeah.
You can look at that. So 0 0 1 0 1 1 0 1 0 0. Let's look at the.
What's the 2 at the end of that?
This just means the space 2. So it's kind of like, remember when we said the 1 plus 1 equals 1 0?
Yeah.
Okay. This is just more of an explicit statement that you're dealing in base 2.
Yeah.
So it's more of an explicit notation. Yes? Because it has to be 8 bits. So if we go back on this, and that's why I was trying to use this, because one of the things that we can do is actually have it expressed as 8 digits. Okay. So if we look at this, so 1, 2, 3, 4, 5, 6, 7, 8. So now the new digit is here. 0, 0, 1, 1, 0, 1, 0, 0. Okay. So that's stands for 4. And then likewise, the same thing happens. This is 1, 1, 0, 0, 0, 0, 0, or greater than.
Does it no good to the next line?
How does it know to get to the next line?
Oh, because we specified the 16 factor.
Exactly. Yep. Gotcha. You got it. But does everybody see where these patterns are coming from? It's coming from the fact that these are being interpreted as binary numbers. Well, first they're being interpreted as ASCII characters, but those ASCII characters have a value associated with them, and we're interpreting them as binary numbers. So I won't go through the rest of them, but just realize that if you actually break up these, put these in 8 bits, and go through the exercise of knowing that this is 42, 52, 62, 72, 82, 92, and then converting it using either Wolfram Alpha or your spreadsheet, you will find that that matches the pattern that you're seeing right here. So, and the reason why this is very compact is that if you look at the size of this, you only have 1, 2, 3, 4, 5, 6 characters. Right? And that's what Blair was talking about, the fact that ASCII data is much larger because it's meant for human consumption, but for a computer, they can read this information more efficiently. And that's why it's usually binary data is a lot more, the price you pay for that compactness, that it's hard for a person to read. So everybody see where this is coming from? So these examples are good because you kind of see, okay, one particular image is meant for human consumption, another image is meant for computer consumption, and computer consumption is not as easy to read, but a lot more compact. So in general, if somebody gives you binary data, it means that it's a lot more, it's a lot smaller, but also harder to read. So, any questions with regard to this, with regard to imagery? So what we'll do now is we'll move over to some of the other topics that we didn't quite catch before Blair came along. But one of the things that you need to understand is the concept of scalable vector graphics. And that's different from imagery that we just talked about. And the reason is that with raster, JPEG, GIF, PNG, there is this particular type of process where you get digitization. It's you get a certain quantization associated with imagery, because imagery is not really a mathematical representation, whereas vector graphics actually has a mathematical representation, which means that no matter what resolution you try to print that out, or you try to display it, it will always have infinite resolution, because you are drawing things based on mathematical expression. Whereas images are not mathematical expressions, but actual digital counts that have been sampled, so to speak. Okay, so there's a sampling process associated with that, and that's why when you actually see something that's SVG format, what we have here is not so much image information, but an actual set of instructions that a computer can now interpret and try to use to actually draw. So the printers will know how to draw that particular format. And if you look at this, what does this format look like? XML, that's right. And that's all scalable vector graphics is that it's essentially an XML. And one thing that I want you to realize is that there's a lot of parameters here that when you look at that, you can read it and say, okay, I understand what it's supposed to do. You can actually look through that and see what's going on for that particular case. And anything that has one of the fonts that you use for different applications, they have something a little more complicated than this, but they actually tell you what kind of curves are going to be generated for that. So another example that we have here is blue magic rectangle. Again, you can actually read through the specifications. And that's why it allows these things to be rendered in infinite resolution, because you're just telling the printer, I have a mathematical representation of this particular shape. Yes.
You know exactly how icon works too.
Yeah, what would you,
If you were to draw a shape, it's the same thing where you just give it, you just have to define the... You
can. So in Python, there's probably different graphics libraries that allows you to do that. So, but this is what for scalable vector graphics, this has been predefined. But that's one of the things that so whenever you have a PowerPoint presentation, it's always, if you have got something that is scalable vector graphics, it's better to use that than to use an image, for instance, like an image of an arrow. Okay, if you have a PNG of an arrow, that will only work to a certain point. But if you use an arrow that's been defined as scalable vector graphics, it doesn't matter what resolution, you'll always get the correct, a well-drawn arrow or graphics. And that's why I bring up those two data types, because in geographic information systems, you have raster for the images, for the aerial images, satellite images. Right? There's no mathematical representation for that, but for streets, polygons, boundaries, these vector graphics is what you would want to use in this situation. Okay. And again, I just want you to realize that it's nothing more than XML. And typically, I'll say, okay, here's a shape. Show me what you think that file will look like. What are the attributes that I have given this shape in the exam? What are the things that you can write to represent that particular? It doesn't have to be exact. You just need to realize that you have to put these types of attributes in your answer. Okay. I typically ask one. Yes?
How are you going to do these things?
So if I say, okay, give me some attributes associated with this scalable vector graphics, so what are some of the attributes that you should be able to tell me? What attributes? So so ignore this. What are some of the properties that you have with what I have here? What are some of the properties of this shape? Size and color. So you would say something like, if you look around here, you can, you don't have, it doesn't have to be exact, but you can say something color equals red. Color equals blue. Shape equals rectangle. I'm not asking you to do this exactly, but what I want you to understand is that you're specifying an attribute associated with this particular shape. Does that make sense? Okay, so yeah, when I say attribute, I'm talking about the properties. Yes. Go ahead. Well, this might be where the rectangle starts. So yeah, and this will be specific to the given type of situation. So if you look at this, one of them is probably starting over here. So this is probably the red one, and then this one is starting 140, 120, probably here. Okay. So yeah, X and Y is where the starting, and sometimes we're assuming that these points represent the top part, and that sometimes is dependent on the different type of shapes. Some shapes may start measurement from the center, and sometimes it's pretty arbitrary. So it really depends on how something's been defined. Okay, does that make sense? Right. Yes. Stroke. Stroke. I think the fill will be the color. And then stroke might be the.
Oh, maybe he said outline.
The outline, because if you look at that, what's this one? It's color, right? Right. And what's that color? Black. Black. See, look at that. You can read hexadecimal now. That's right. So this one, let's look at this. Let's just say it is red, green, blue. So the style is fill. So what this is saying is I have a shape, and the fill is the color. So, and we said that hexadecimal is a sort of a compact way of representing colors. So the first two digits are for red, second two digits are for green, and the last two digits are for blue. And no red, no green, lots of blue. Because F is hexadecimal for 2.5. Well, if FF, so if you think about the numbering system, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. F is like the highest value.
Oh, is that all that way?
That way. Yeah. A, B, C, D, E, F, yeah.
How come it only goes up to F?
Because you defined it to be 16 hexadecimal. So 16. If we had defined it as something else, so instead of 16, something like base 18, we would add a few more symbols. A few more symbols. It's, you mean in alphabet, but in hexadecimal, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So it's a numbering system. Don't even think about alphabetical. Yes.
It also has something to do with IPv6.
IPv6, it does, okay, because what it tells you is how many, so to actually, if I only had 8 bits of information, how many unique values can I generate? No, I mean, that's a legitimate question. It's like, if I only have 8 bits of information, oh, so step back. I only have 1 bit of information. How many values can I represent? 2. Okay. If I have 2 bits of information, how many can I represent? 4, right? So you just keep moving that up, and that question is, if I have 8 bits of information, how many values can I represent? Actually, it's 256. 2 to the n. 2 to the n, where n is the. So the internet is based on 4 numbers. So let's actually step back. And if I say something like, what is my IP? The IP address is essentially, think of it as a social security number for every computer or every device that's on the internet. Right. So what this is saying is that our location here is 173.255.253.219. That's for this specific computer. Well, you can see that we have a whole bunch of combinations here. There's a bunch of combinations here, a whole bunch of combinations here, so on. We're actually running out of these numbers, and that's why when you mention IPv6, that's actually what's going on. They now need to add several more digits there in order for you to be able to uniquely identify all these different devices. Does that make sense? That's why in color also, for grayscale, you only have 256 values. Red, green, and blue, you have 16 million colors. It's about all the combinations of red, green, and blue. And this is where binary numbers come in, because this also tells you how many internet devices you can have. Location. So this whole binary thing actually has some value. Yes?
Is the max value on that 256?
Correct. Yes, it is. It is for each of these.
Yeah.
Yeah, exactly. These are all 8-bit pieces of data. Yes, 255 is one of those numbers that you just have to keep in mind. So, let's see. Where was I? No, those are, you guys are asking a lot of good questions with regard to that.
But if it's 8-bit, why is it 255 and not 256?
0. Start at 0.
No, that's it.
Yes, forgot about 0, and that's a common thing that people run into. Is like when you do counting in terms of computers, it's always starts at 0. Yeah, and naturally, most people want to start with 1, just because I think when our brains back in caveman days is like we didn't have the concept of 0. It's either it's 1 is something, and that's again that's something to sort of keep in mind. What was that? I was in scalable vector graphics. And I lost that. Oh, I know. Sorry about that. So, is everybody comfortable with the difference between scalable vector graphics and raster imagery? Those are the two things that will come back to haunt us when we start doing some of the more GIS-related type of labs. see what else remember what else I had on the slide. Okay. Often. All right. So let's talk a little bit about some of the features in GIMP. I'm not an artist, so a lot of the things that I do with GIMP is very rudimentary. There are only a few things that I always tell people that other people have better use of than I do. So let's just open a file that I just downloaded on my desktop, and that is of Lena. And Lena is one of these images that is used by people back in the 70s, 80s for image processing, so it's sort of like a test target that people use. Now, the one property that has to do with images, and it's actually applies not just to this images, but also to anything that has to deal with data, is a histogram. So let's actually look at the histogram of this image, and we'll talk a little bit about that. Right. That's kind of a bad example, but the histogram basically says I go from 0 to 55, 255 values. How often does zeros occur? How often does 1 occur? How often does 3 occur? And so on and so on and so forth. And what you have there is essentially a histogram of an image. That's actually very useful because it allows you to actually enhance images based on that type of statistic. You can stretch things out. So if I actually try to modify the darkness of this image, you can see the histogram sort of change. So if I say, if I decide to change the brightness and contrast here, you can see how the histogram is changing, because what you're doing is you're basically moving these pixels from one gray value to another set of gray values. And when I move that, I'm basically moving it. When I'm brightening it up, what I'm doing is I'm taking all these pixels and moving it into a higher value. Likewise, doing a contrast, what you're doing is you're sort of squishing the number of values. This is sort of a bad image to show, but what you're doing here is you're seeing the histogram being changed, right? So that's one of the things. And this is something that we'll actually see not just in images, but also in text. One of the things that we'll be doing in Python is coming up with an algorithm that will go through and count how often a particular word occurs in a document. What good is that statistic? Anybody know why we would want to do something like that? No? Okay. What do you always see sometimes when you Google? See trending topics. What is a trending topic? A trending topic basically says, we're going to show you this particular topic because it's occurred many more times than any other word. So that's one of the things that you will use histograms for, is trying to understand how frequently a particular word is being mentioned on the internet. And you can use that as a means to actually specify what a trending topic is. So what you're doing there is essentially, as you're getting all these words, you want to count how often is a word being used by a person, okay, or being used by the internet. And that's where you would use a histogram to actually count that. And that's one of the things that we'll be doing in Python to actually show you that you can do those kinds of counting. In images, you do the counting of each of those pixels. How often do they exist in that image? And that's a statistic that is actually very important because it allows you to actually modify the brightness of a given image. So you probably see a lot of the CSI type of situations where they say, oh, zoom and enhance. And that's what they mean by enhancing something, is to adjust the histogram of an image so that you can see a lot more information. So as far as spatial processing is concerned, the one, and as you can see, there's a whole bunch of things here. The one that's frequently used, and I'm trying to remember which one it is the fuzzy select tool. And the fuzzy select tool, let's see if I remember which one it is. Scissor select tool. I'm trying to remember now. Oh, is it this one now? Free select tool. Fuzzy select tool allows you to basically start at a given point, and then it will try to essentially come up with an area based on similarities. So in this case, this allows, and it's not always perfect because there are differences. So what it did is just it basically allowed you to select this particular region. If I wanted to start it at a given area, let's try that again. Use the fuzzy select tool. Let's unselect that. And I wanted to just select this particular area right here. Right. You'll see that's a little more, it's easier for it to actually, for you to actually chop out that particular area. So in this case, you can then say edit, cut that out, right? And you can paste that in different regions. So the fuzzy select tool is probably the one that I use the most because what it does is it allows you to quickly be able to specify certain regions. And that region is essentially an algorithm goes through and tries to figure out, okay, what are the different pixels that have the same value from the one I selected? And then they'll just grow that region. So, so the fuzzy select tool is one that I use frequently. The other thing that you also have with GIMP that I'll go over very quickly is the ability to create layers. So sometimes what you want to do is you want to establish a graphics layer, for instance. So you may want to put a new layer, right? And that new layer is someplace where you would include some sort of text, right, so that you can easily change, so you can hide the different layers and then include text, for instance. So this just allows you to be able to move things around instead of having to work on the image per se. It's easy to essentially think of it as having different types of layers, kind of like cellophane on top of each other, and you can move this around, you can modify that. So the use of layers is very useful because it doesn't destructively change the image that you're putting something on top of. So, and in order for you to save this, however, as a PNG or as a JPEG, you have to what's known as flatten it, which means that the text that you put in there becomes a part of the image. It's hard now to actually try to modify that. So in some cases, what people will do is actually use vector graphics instead to represent the text. All right, that's all I have for today. And next class, we'll touch a little more on data and some of the things that you want to know with regard to Wolfram Alpha. kind of touched upon it now, but there's a couple of other things that I want people to at least be aware of with Wolfram Alpha. Okay?